Hello and welcome to my channel. Today we will discuss some points in 9th chapter current electricity from new syllabus physics 12. So first point is the Kirchoff laws. In year 1845, Kirchoff introduces a set of laws which deals with current and voltage in electrical circuits. There are some electrical circuits that can be reduced by using formulas of series and parallel combination of resistors. We can convert that circuit into one equivalent resistor. But there are some complex circuits which cannot be reduced by using this parallel and series formulas of resistors. So Kirchoff introduces some laws KCL and KVL. By using these laws we can reduce that complex circuit, or we can find out some unknown current and voltages from that complex circuit. Before going to KCL, Kirchoff's current law, we discuss some terms used in an electrical network. So here is one example of electrical network. First term is a junction. Any point in an electrical network where two or more conductors are joined together is called as a junction. Here there are two junctions A and B. At A, three conductors are joined together at this one point A. Okay, so A is a junction and also B is a junction. Here also three conductors are joined at one point. Next term is a loop. Any closed conducting path in an electrical network is called as a loop. Any closed path where current flows. This path in an electrical network is called as a loop. It is also called as a mesh. So there are two independent loops in this electrical network. One loop is this. If we consider points here A, B, C, D, E and F, then first independent loop is A to B, B to C, C to D and D to A. That is A, B, C, D again to A. This is one closed loop. Another closed loop is A to F, F to E, E to D, again D to A. That is A, F, E, D, again to A. This is another independent loop. Okay. So in this electrical network there are two independent loops. Next term is a branch. Branch is any part of network that lies between two junctions. There are two junctions A and B. So here is one branch. So R, cell of EMF E1 and again R. Second branch is this resistor and cell and to B. So here is the second branch, and third branch is this R, cell of EMF E2 and again to B. So this is a third branch. A branch is any part of a network that lies between two junctions. In these two junctions A and B, between these two junctions A and B, there are three branches, 1, 2 and 3 as shown in this figure. Okay. Next, consider two series resistors R1 and R2 connected with this point, node or a junction. Okay. First, before going to KCL, we will discuss the law of conservation of charge, because law of conservation of charge leads to law of currents. So how we will discuss here. R1 is one resistor, R2 is one resistor connected in series with this point or a junction. Current flowing through R1 is I1, and let's say current flowing through R2 is a I2. We know that when resistors are in series, current flowing through these resistors are equal, that is I1 is equal to I2. But we can prove it by using law of conservation of charge. Electric charge can neither be created nor be destroyed. The amount of charge remains the same. That is, if we consider a Q1 charge per unit time, t is arriving at this junction, Q1 charge per unit time t, that is current I1 arriving at this junction. For law of conservation of charge, same amount of charge, or we consider Q2 per unit time t is leaving from this junction. Q1 by t, Q1 charge per unit time t is coming towards the junction, and Q2 charge per unit time t is going away from the junction. By law of conservation of charge, same amount of charge must leave the junction per unit time. Okay, that is, as the amount of charge remains the same, incoming charge is a Q1, outgoing charge is a Q2. Q1 by t is equal to Q2 by t, as the amount of charge remains the same. And Q1 by t is I1, Q2 by t is I2, therefore I1 is equal to I2, that is incoming current is equal to outgoing current. Okay, here I1 and I2 are same. We know that in series combination of resistors, current flowing through these resistors is same. But if we consider the third resistor R3 shown here, then the current I1 arriving at this junction, I2 leaving from the junction and flowing through R2. But here I1 is not equal to I2 because some current flows through the R3 also, that is I3. Charge Q1 coming towards the junction per unit time. Q2 charge flowing through this resistor R2 and Q3 charge flowing through this resistor R3. Okay, so by law of conservation of charge, amount of charge remains the same, that is incoming is equal to outgoing, because charge never be created nor be destroyed. That is, Q1 upon t is equal to Q2 by t plus Q3 by t. Q1 by t is equal to Q2 by t plus Q3 by t. And Q1 by t is I1, Q2 by t is I2, Q3 by t is I3. Therefore, I1 is equal to I2 plus I3. Here, I1 is incoming current and I2 and I3 are outgoing currents. So, here, incoming current is equal to outgoing currents. Okay. Now, we will discuss the statement of KCL. Here, consider one point or one junction P. At junction P, there are 5 conductors, 1, 2, 3, 4 and 5. Current flowing through first conductor is I1, then I2, then I3, I4 and I5 respectively as shown in the figure. I1 and I2 are incoming currents and I3, I4, I5 are outgoing currents. The statement is algebraic sum of currents at a junction is 0. Algebraic sum of currents at a junction is 0. At this junction, algebraic sum of I1, I2, I3, I4, I5 is equal to 0. We can generalize this formula as summation I is equal to 1 to n, I small I is equal to 0, where I small I, that is It is a current in ith conductor at a junction having n conductors. If we consider there are 5 conductors and I2, if we consider small I is equal to 2, then I2 is the current flowing through the second conductor. Okay. The statement contains word algebraic sum. Okay. What is mean by algebraic sum? There must be some sign conventions related to these currents, that is arriving currents, or we can say it as the incoming currents. We consider these currents as a positive, and for leaving current we consider negative sign. Okay, for leaving or outgoing currents we consider the negative sign. Arriving or incoming currents are I1 and I2. Therefore, we consider I1 and I2 as a positive, and leaving currents, that is outgoing currents, I3, I4 and I5, we consider their signs negative, and algebraic sum of all these currents is equal to 0. I3, I4 and I5 have negative sign. If we transfer it to the right side of the equal to sign, then we get I3 plus I4 and plus I5. I1 and I2 are incoming currents, I3, I4, I5 are outgoing current. Therefore, incoming current is equal to outgoing current. Okay? Incoming current is equal to outgoing current. So remember, Kirchoff's first law, that is Kirchoff's current law, is consistent with conservation of electric charge. That is, some charge is received, that is Q1 per unit time due to current arriving at a junction. For conservation of charge, same amount of charge, that is Q2 plus Q3, same amount of charge must leave the junction per unit time, which leads to the law of currents, that is incoming is equal to outgoing. Okay. Thank you.